We can start. Okay, so I'll just introduce Kirti, our first speaker. So one sec. Kirti Sankhala is a first year postdoctoral fellow, originally from India, currently studying at the Technion in the lab of Azrieli alum, Tamar Segal Peretz. She'll be speaking to us today about efficient membranes, future of clean water. Kirti, it's over to you.
So I start now. Is it okay, Michal? Okay, great.
Perfect, yeah.
Okay. Good morning, everyone. Thank you, Michal, for the introduction. So I'm going to talk about efficient membranes, future of clean water. So as you can think that I work on membrane technology, which is used for, in particular, application of water filtration. So we all want a safe glass of drinking water, but as you know that the population is increasing exponentially, but on this planet Earth we have limited fresh water supply from rivers, lakes, and groundwater. So with increasing population we can expect that we will have water shortage. So how does water shortage affect us? So it not only affects at personal levels, but it can significantly contribute to a country's economical situation. So absent insufficient water and sanitation enforces use of contaminated water, and which can transmit diseases which can be easily prevented, like diarrhea, cholera, and all the virus or bacteria related diseases mainly. And if these can be easily prevented, then we can do it with efficient separations. So alternative water resources are needed for the growing population, and so that everyone can have safe and potable water. So when we talk about water filtration or purification, what are the pollutants in water which we are talking about? So as we all know nowadays, a big concern is viruses or bacteria. Then coming from our urban lifestyle, we have generated a lot of microplastic from our uses, from clothing. We use a lot of plastics. Then a lot of pharmaceuticals, which is going to develop this recently. The very hot topic is antibiotics resistance. Then there are a lot of chemicals coming to our water supply from industries and also volcanic eruptions. So these are the pollutants which we care. And when we talk about water purification, then the two major things which we want is, first, high purity. We want high rejection of all these unwanted species which are threat to human health, and at the same time we want high productivity, which means we generate more of clean water in less energy and time. So at this point, membranes are performing much better than other available resources. So here you see a scanning electron micrograph of a membrane surface. So it is a layer which has these tiny holes which are called pores. They are, here you see a scale bar. So these pores are around 25 nanometer. So in this membrane, what you see that certain things can go in and certain things can be rejected. So with water, the things which are less than 25 nanometer in diameter, they will go through, but things which are bigger than 25 nanometer, they will not go through. So, but the major concern for the future water purification is all about chemicals, pharmaceuticals, dyes, which is a lot is from textiles, and then the pesticides which are widely used and more than required. So all these contaminations are of size less than 10 nanometer. So which means we need to filter things at molecular level. So this is surface of a nano filtration membrane. You don't see a pore. This is a high resolution image. So the pores are of size 1 to 10 nanometer. These membranes are used for molecular separation to soften and disinfect water. When I say soften, it means that I don't want to see the salt deposition in my kettle. So 4 dimensions. So this filtration, which we do at molecular level, it is highly affected by the charges, the electrostatic attraction or repulsion between the molecules and membrane surface. So these things are highly affected by, this filtration is highly affected by charge, pH of water and temperature. Currently there are membranes, it is widely applied, but there are challenges that the membrane surface is having more negative surface charge. The surface, which means that the surface attracts all these unwanted species, and then they are less hydrophilic, which means they don't like water much, but they like all these salts on the membrane surface, and which makes these membranes less efficient because they are fouled very easily. Everything accumulates on the surface and we can't get much water through the membranes. So how can we change the membrane surface? We all know that brush it with what you want, but it's not that easy because we want coating at nanoscale. So it should be nanometer thick so that we can reject this unwanted things which are of nanometer size. How we can do it? For this we have a technique called atomic layer deposition. As the name says, that we are doing deposition at atomic level, and we are particularly doing deposition of tin dioxide on nanofiltration membrane. Why we are doing ALD? So this is a transmission electron micrograph, and you can see that how conformal and nanometer precise coating we can achieve with atomic layer deposition. So this allows us to have a membrane which loves water and at the same time which can reject the salts. So so this is a membrane, again the scanning electron micrographs of the membrane before ALD, and this is after ALD. You don't see much of the pores because they are highly dense, and but we can see that how we can see the tin and oxygen. For that we do scanning electron micrograph with elemental mapping of energy dispersive X-ray spectroscopy, and then we can see that the tin is in red color and oxygen is in blue color, and we have tin and oxygen everywhere on the membrane surface. So finally we have this ALD modified membrane for efficient water separation. With that we have tuned surface charges. Now our membrane is less negative than before, which means that the foulants of salt and bacteria and all will not be attracted much to the membrane surface. With that we also tune the pore size, and we can selectively remove the salts. I hope that there will be less salt deposition in the kettle afterwards, and high productivity. When we change the surface chemistry of the membranes, we can have better water flux in less energy and time. So with this technology we can promise a future for clean water for everyone. Thank you very much for your attention, and I thank Azrieli Foundation for supporting my research work.
Do you want to take down your presentation, Kirti? And Kirti is open to questions.
Hi, Kirti. How do you pump the water through membranes? Do you need to apply some pressure, or just diffusion?
Yeah.
Because
no, we need to apply pressure. In nanofiltration, it is less. It is around 5 bar. But as the size of the membrane pores get smaller, we need more and more pressure to push the water through the membrane. But when we change the surface chemistry, as I said, that after that the membrane loves more water, then with changed surface chemistry we will we get more attraction for water. So in this way, it helps to save energy.
And what is advantage comparing to these membranes we use in biology, like PVDF or?
So those membranes are PVDF is a very hydrophobic membrane. So PVDF literally hates water. So when we work with nanofiltration, then we really need to have a water loving membrane because the separations are going through polymer chains. So imagine it is a polymer network of loose chains like threads, and then your water molecules should go through, but not the bacteria and all, although they are pretty big. But so in this way, when you have a hydrophilic polymer which loves water, then it's much easier to get through. But PVDF is quite hydrophobic.
Thank you.
Yeah.
I have another question. Applicatively, where in the chain of water supply would you say you see these filters being applied? Is it in every home, in the access of water to the home? Is it before that in main junctions?
Maybe just before you answer, Kirti, Aldema, do you want to just introduce yourself? Because Kirti knows Slava, but I'm not sure she knows you.
So I'm Aldema. I recently opened a lab in Tel Aviv University in the Faculty of Life Sciences, working on RNA modifications.
I'm working on, sorry?
RNA modifications.
Okay. Yeah, nice to meet you virtually. Yeah, so the actually at homes in Israel, I think it is the water is already purified by the municipality. But for example, it's not everywhere like this, and in many places you need to have it just before you drink. So you need to have your purifier at home. Here also, I know many people have at home, and then the commonly used purifier is reverse osmosis. And reverse osmosis, maybe you might have noticed that when the purifier is working, there is always some water is going through the waste, which generates a lot of waste and it consumes a lot of energy as well. So if we have a nanofiltration, it can work at home, and it is already applied in many places. But the best way is like if you have a pollutant, like just use the polluted water, because at the end water purification itself is very expensive if you do it on huge scales. But just using a pollutant, for example, outside the industry. So like if the industrial waste is treated within the building and then it comes out, this is the best solution to save energy and to keep the environment safe. And for example, the major concern of antibiotic resistance is coming from hospitals, and these where patients are living mainly. So if somebody just treats that water, and then only if the water is discharged, that is the best way.
Also, Kirti, what does make water tasty? Like, is your water tasty?
You saw my kettle, so it has a lot of salt. So yeah, but in all the hot countries, when there are bacteria and this biological family is growing in water, then sometimes there is also you feel the smell, or and then they put a lot of chlorine, and so these are the time, and all these things are at nanometer level. So nanofiltration is something which is going to be future for everyone, because the water is getting more and more polluted, and even the groundwater is getting toxic in many parts. And with, for example, you might have heard the stories that now we have arsenic in rice. So because how the arsenic goes through rice is like first the industries are generating arsenic, so industry is not treating their water, they directly discharge it. They discharge it and then it sieves through the top layer of earth to the groundwater, and then it travels afar from that place, and then it is supplied in agriculture, and then and rice is a crop which needs a lot of water, and then it ended up in our food chain, and it's highly toxic.
Can you put electrolysis in some step of your pipeline just to get rid of the ions?
You can't do much in the pipelines because sometimes the pipelines itself are contaminating. So you might heard, it was a very popular news in United States that they have very great pipelines which is supplying water throughout the country, but when it was summer and they had put a lot of chlorine in the water, and then this chlorine got reacted with the pipeline of copper and something, and because the pH of water turned a bit acidic, and then at the end it was very unsafe to drink that water. They highly contaminated the water supply. So you can't do much with pipeline. It needs to be checked at the end of the pipeline. So as there was question before that where we should put the water purification, so I would say that in future it's going to be at home, because means the way itself is polluted.
What about costs? Is this going to be something very expensive, or I mean, is it feasible? Can people at home just use these kind of filters?
Yeah. In India, almost every household in my place is having reverse osmosis. So when there is this industrial production, then it is not that expensive. So it will cost like 200-300 shekels, and then everyone have it at home. But yeah, electricity you pay additional. But one time you buy it in maybe less than 500 shekels. It should be cheaper than that also. Yeah.
Additional questions for Kirti? Okay, thank you, Kirti.
Emmanuel, you had something to say?
Yeah, maybe. What is the size of your experimental setup?
So for experimental setup, now I use membrane, which is of my handy size, so like this size, so around 14-15 centimeters square, and I do one membrane at a time. But my aim is like I work in a US-Israel consortium, which is a joint project between some United States universities and laboratories, and in Israel also. So I am doing here lab scale studies in Technion, and then at Argonne National Lab in the same project they are building a larger facility. So I hope that once I complete my study here at lab scale, then we will have the larger production of the same membranes and characterize at Argonne National Lab. That is long run, and in the same project there are industries involved. They will take it even further higher.
Okay.
Yeah. Thank you, everyone.
Thank you. Thanks, Kirti. Thank you very much.